have your microphone? Ah, you can use use that one. Okay.
Yes, it's working.
All right, so thank you all for coming. This is the last day of the workshop. Thanks for being still here. Just a couple of organizatorial and logistical pieces of information. So we'll have 2 sessions of lightning talks today. That means 1 hour of talks. You can find an updated flyer with the lightning talk titles on that desk over there. The format of the lightning talk is the same as yesterday. 5 minutes talks, 2 minutes questions. We'll have coffee served at 3 p.m. today, half an hour earlier than usual. And at 3:30, we'll have a discussion on where to hold the next Einstein Toolkit school and workshop. So if you want to come up with suggestions, this is now your time to think about them. Let me please also remind you that we have this Woman in HPC talk that's going to happen in this building next door at 1:30 p.m. So if you want to join, go over, have a look. And that is, I think, everything that I have to say right now. And with that, I let Ian introduce our first speaker.
All right, okay. So the first speaker of the day is Chen Xiang, and she will talk about Data Vault and Einstein Toolkit Data Repository Design Update.
Okay. Morning, everyone. Yes, as the title says, it's about the Einstein Toolkit Data Repository Data Vault. So we'll talk about this later. So overview of the project. Data Vault is part of the ISI2 bigger projects, which last 5 years. The currently is the 2nd year, and is a collaboration among different institutions. And so the timeline for the Data Vault right now is to prototype and initial development of the data repository. So the overall goal of the Data Vault is to provide a platform for the Einstein Toolkit and users to share and publish their dataset. And in the meanwhile, they can use the online data analysis and visualization tools to compare the results, and also for the computational reproducibility, and also to explore more discoveries. So similarly to the other data repositories, we try to associate DOI for each dataset with a permanent link, and also all the formats, there are open formats for the easy access, and also we try to provide a relationship among different research objects, and also the metadata is searchable to enable discovery. So why the dataset is unique is Data Vault is unique is because it is domain specific and it's community centric. So we try to provide a large storage solution for the very huge data sets from the simulation data. And also, this is is to enhance the reproducibility research. And also we try to provide online data analysis and visualizations. So the 2 design tasks for this Data Vault is, first one is to the data sharing workflow design, including deposit and user access. The second design task is about online data analysis and visualization tools is going to be designed. So we build all these features and functionalities on the Galerkin infrastructure. So the current status, as we talked briefly yesterday, is that initial design of the interface mockup is completed and it's ready for the implementation. And right now we have one Galerkin plugin development is ready to use for it's called the Vega Lite for the data analysis and visualization. So here I will show the repository interface mockup. So the idea here is that we are trying to provide, basically, the first line here is about the data deposit stages, including description, upload your files, and the review stage, and then publish your data set. The second line is about the data and user data access, about the download and the reuse of the data set. So here is the mockup of the the homepage of the Einstein Toolkit Data Repository Data Vault. So here we mentioned that the DOI association and minimum maybe 5 years of support and curation of the data set. and also support online data analysis and visualization. So in order to deposit your data set, we require people to log in. So either you log into this repository or you need to sign up just for once. And the deposit design here is that before you actually deposit anything here, we try to give you an overview of some considerations. So you need to consider about your dataset license. You need to think about at least one primary long-term contact for a dataset. And also, if you want to delay your publication or just publish them intermediately. And also we try to provide some help anytime. So after you have such considerations, so you need to agree to the deposit agreement, and also you have to make sure that you are the author or you have been given the permission to deposit this data set, and there is no any sensitive or private information in this data set. And then, when you click on those, you have this page for the deposit. So the dataset the title is required. The license you can choose from the drop-down menu, and also the first name and last name of the authorships, and the email address and primary contact is required. The dataset description is optional, but we suggest or encourage people to do that. The keywords, we'll talk about this later, and the publication delay options is we have intermediate publication or the file-only embargo. And then the founder information and the relationship to other research objects is also optional. And then here is the file upload. So the keywords is about the the type of data and just the data sets of the objects are in the data sets and publication delays here. So after you type everything here, this is just a realistic data sets from the Einstein Toolkit infrastructure. So this is the real data set. So we have the publication delay for this data set, and also we have the waveform data set is uploaded. Then this is the review page. Basically, you have the citation, what it looks like, and also review everything. And we also provide a preview of your data set if possible. Then you publish your data set. Here it did mention that it's going to be available for the data set until October in 2017. So then a pop-up window about your data set is successfully published. So at this point, data set metadata is available to the public, but the data files are still embargoed. So I will stop here because I don't have much time. So I'll talk about this later, and any questions are welcome. And yeah, we have the working group discussion later. So
we'll have a discussion later. So if people are interested, then we can talk. So if we have time for a brief question.
Yes.
I have a comment. I think it would be. I just have a comment. I think it would be nice if we had a. I am speaking into the microphone. I just think it would be nice if we had like a little tutorial where we all uploaded some toy data set just to get familiar with it at some point. I don't know when, but just rather than watch you do a presentation on it, would be nice. I mean,
you mean
just to become familiar with punching the buttons and how it works. I think it would be useful to have like a little hands-on tutorial for this kind of thing at some point.
So the slides will be available, right? So
slides are
here,
available, and the real implementation is not ready yet because it's still, right now it's the interface markup. So, we're going to implement later, but this is just, what it will look like in the future, and that's why we need your feedback.
I didn't realize that. Okay.
Yeah. So
I think we need to get on because we've got a lot of talks and we're already quite over time. So. Thank you very much. All right, and the second talk is Andre de Silva Schneider.
Yep.
Okay, an open source nuclear equation of state code for astrophysical simulations.
Okay, thank you all for being here this Friday morning, and thanks for the organizers to give me the opportunity to talk a little bit. It's something completely different, I guess, than what's been talking about the rest of the workshop. So recently, with Luke Roberts from Michigan State and Christian Ott at Caltech, we developed this code to obtain the equation of state of nuclear matter so that you can use them on astrophysical simulations. So here I think the equation of state is just a thermodynamical properties of matter as a function of density, proton fraction, and temperature of the system. And the reason we care about that is because it has a lot of astrophysical relevance when you're simulating core collapse supernova or binary neutron star mergers and so on. And one of the difficulties of obtaining a consistent equation of state to study this phenomenon is because it spans a wide range of densities, as you can see in this figure, like a 15 solar mass star that undergoes core collapse supernova. Its temperature changes by about 10 order of magnitude. The temperatures change by about 2-3 orders of magnitude, and the proton fraction changes from symmetric nuclear matter, you can see on this box here on the right side, from about 50%, where you have the same number of neutrons and protons on matter, to very neutron-rich matter, where the proton fraction is below 10% or so. So here's a schematic picture of what the equation of state looks like. So if you get a proton fraction and you have temperature on the vertical axis and density on the horizontal axis, you can get these three types of phases. And this is a very schematic picture of on phase one, you get a low density regime where at high temperatures, or you have very light nuclei, such as alpha particles immersed in a neutron and proton gas. And you also have electrons and photons around. If you lower the temperature or increase the density, you start getting heavy nuclei. And then if you increase the density a lot, the heavy nuclei dissociate, and you basically have a very dense gas of neutrons and protons. This is a long-standing problem in nuclear physics. You combine several different people from several different areas combine to try to figure out all of the properties of dense nuclear matter. So you do some heavy ion collisions experiment. You can do nuclear reaction experiments. You do simulations of astrophysical phenomena. That's what we're interested in here. And then you also have theoretical many-body calculations. And even with all these efforts, you still have a lot of uncertainty. If you go to very high densities, such as the ones that you find in the interior of neutron stars, or that right before a proton-neutron star collapses into a black hole, you don't know basically what the equation of state is. Also, there are if you have very neutron-rich matter, you also are not don't have many constraints on the properties of nuclear matter. So how do we obtain a hot, dense equation of state that you can use on the simulation? So you can choose from several different models. Here in our case, we use a non-relativistic model, use effective potentials for the interaction between the protons and neutrons. And for now, we don't include muons or pions or quarks at high density. So our model is based on the Latimer-Swesty equation of state. So if you've done simulations of core collapse supernova in the past or neutron star mergers, you probably use this equation of state. We generalize this so that whenever you have more constraints on the equation of state, such as the properties of nuclear matter at higher densities, you can upload these constraints into the equation of state code, and you obtain a new equation of state. And then you can use that on your simulation. So the code is open source, is available at this link here, and we recently put our paper on the archive. So I'm going to quickly go over a few of the results. So for example, you have all these parameterizations for the nuclear force that are available in the literature. And we got 10 of these over 250 parameterizations that there are. And we try to obtain the neutron mass radius relationships of neutron star. And you see that only a few of them actually reproduce this mass of a neutron star that was recently observed. So we have 2 solar mass neutron stars out there. And most of the equations of state that we have that have been used in simulations are not able to reproduce this limit. So you want to only use equations of state that are able to do that in your simulations, right? Okay, I have 1 minute. So we also study spherical symmetric collapse of 15 solar mass neutron stars. So here in this picture, you see how the density and temperatures at the core change depending on the equation of state you use. And you can see that certain equations of state produce much lower temperature at the core than other equations of state. And this might have an important signal on the size of the proton-neutron star formed, the gravitational waves that the neutron star emits right after being formed, and the neutrino signal. It also changes. So now we did simulations for a heavy star for the solar mass star collapsing, and we see also the time to form a black hole after bounce also changes a lot depending on the equation of state you use. Okay, so thank you very much. I guess I have 10 seconds, and these are some.
Thank you very much for sticking to time. Any questions?
Yes.
So with your equation of state, if you want to incorporate it into the Einstein Toolkit, I guess you have to provide a little bit of glue code, or do you already have that given that
I
you're
don't
working
have that. I believe I talked to David Radish, and he said he has a code that could do that, since I used the format that's already on some previous equations of state use. So I'll talk to him and know that.
And then a similar question to how low densities do you go with your equation of state?
So I'm used to thinking in baryons per Fermi cubic, and that's about 10 to the minus 13. I believe that's like 1,000 grams per centimeter cubic, more or less.
So very low, thank you.
Yeah.
Okay, we have time for more questions. No? Okay, then I guess we thank the speaker again and take advantage of the extra time. Okay, so the next talk is Shore Abdolrahimi from California State Polytechnic University, and she will talk about spectral methods in general relativity and large Randall syndrome to black holes. Please.
Good morning. So just a small warning. This method is different from the pseudoscalar method, which is used in SXs. So Randall syndrome model, in Randall syndrome model, we have a bulk metric which satisfies the 5-dimensional Einstein equation with negative cosmological constant. And we have a brane which represents our world in this model. And this is a thin brane which satisfies this Israeli junction condition, which means the difference between extrinsic curvature on both sides of brane is proportional to the induced metric on the brane, with this proportionality related to the cosmological constant. This condition is especially defined in order to have a Ricci flat metric on the brane. Brane world scenarios provide geometrical interpretation of hierarchy problem, and our world is just a domain wall and that brane. Of course, one of the most important questions for these models is if they admit black hole solutions, especially large black holes that we know astrophysically exist. So this has actually been a decade problem, and now I'm presenting the result. It's a bit old, but I found this the most suitable for this workshop. So during this decade, there have been many groups who attempt finding the solution for this large black hole, and their attempt had failed. The method that was used usually was to reduce the problem to elliptic equation for metric functions, and then use relaxation method to find it, which was successful only for finding very tiny black holes, that their radius is very small compared to the bulk curvature scale, which don't have any astrophysical implications. So now, in actually 2011, we presented our result in a conference in Niagara Falls that these black holes exist and shown how they are. Shortly after that, actually, another paper appeared in arXiv. This one, they use a totally different method for constructing the solution using Ricci flow, and I don't have time to talk about the other method. Then we went ahead and compared all our results with theirs, which they were very kind to provide it, and show that we have agreement with their solution. The method we used is a bit robust, but worked really well. So we consider this metric ansatz. We constructed this metric ansatz specifically such that these functions now A, B, C, and D are polynomials. And we impose these boundary conditions on the boundaries. Then we even go further and rewrite this function in terms of now 6 other polynomial functions, which guarantee that the regularity conditions are satisfied on boundary, and Einstein equations are also to the lowest order satisfied on the boundaries. So with this in hand, all we need to do is to find the coefficient of these polynomial functions. And we did this by using optimization method, which was, okay, we define a new tensor, and if Einstein equation is satisfied, this tensor is 0 everywhere. So we define this integrand. If you integrate it over the whole volume of space-time given for time, we use period 2 pi for Euclidean signature. Then we need to minimize this integral. And since this is positive semi-definite, it is when Einstein equations are satisfied, we get I minimum and getting the closest to 0. For integration method, we used Gauss-Lobato quadrature, and our optimization was unconstrained nonlinear optimization. And you see that we up to 6th order that we went, this error decreased, and we found the solution. So after that, we found the infinite mass black hole, and we were able to, with perturbation, find also large black hole solutions. So this brings me to the conclusion that I just want to say that sometimes maybe we need to use different numerical methods and do some analysis before we go ahead and do the numerics. That is all you know. All of you know this. Thank you very much.
Thank you. We have time for questions.
I stay here.
You stay here? OK.
Is it OK?
You have the microphone? Yeah. Any questions?
So is there anything special about lambda equals -6? Minus 5.8 would also work?
No, not really. We can choose any value. This is a scale. It would be the same.
So in the minimization scheme, what method do you use for the numerical minimization?
Unconstrained nonlinear optimization.
But what method?
What do you mean? This was our method.
So it's a local method or a global method?
Local.
Local. OK, so derivative-based. I see. Yes. OK. Any more questions? No? OK, then let's thank the speaker again. All right, and the next speaker is Josef Slochauer from Rochester, and he will talk about puncture-based evolutions of highly spinning black hole binaries using the Einstein Toolkit.
Okay, thank you. So I'm just going to give you a little bit of an update about results that we've had using the Einstein Toolkit, codes based on the Einstein Toolkit to evolve highly spinning black holes. Let's see. So the basic idea is that, so we know that conformal flatness prevents, using conformally flat data prevents one from evolving black holes with spins higher than around 0.92. The SXS collaboration showed many years ago that if you used conformally Kerr data, and in particular Kerr and the Kerr shield gauge, then you can generate spins seemingly as large as you want. And evolve them, but nobody has previously been able to do that with the puncture approach because we didn't have access to the data, so we didn't have any way of even testing to see if moving punctures-based codes would actually work. So at RIT, we developed, we used starting from the Ansorg's 2 puncture thorns, we basically developed, we implemented solutions to the momentum constraints for non-conformally flat backgrounds. And in particular for conformally Kerr, where we start with Kerr rather than in Kerr-Shield, we started in a puncture gauge. We boost it, and we superpose, and then solve the constraints. And basically, what happened, we've shown that although the system right now is not yet efficient, it takes a long time to solve the data. It takes a long time, even once you solve the data, it takes a long time to put the data on the grid, mainly because we're not being very sophisticated in our approach to actually solving the elliptical system. But basically, the system will work. So let me just basically show you. This is a spin 0.99 binary. And basically, what we see is that you have you can evolve it. You have preservation of the spin and mass of the black hole. And if you evolve it, you can then get waveforms coming out, and we compare the waveforms to an SXS waveform. They had previously done a spin of 0.99, so we just read off from their catalog. And you can see the agreement between the L equal 2, M equal 2 on top, and L equal 3, M equal 2 on the bottom. So we have relatively good agreement between two modes. So in detail, the disagreement basically comes from eccentricity. We basically did a solve of our data and went with it rather than doing any kind of eccentricity reduction. So if you look at the residuals, so the top panels are basically showing the difference between the RIT and SXS amplitudes and phases. You can see the oscillations occurring on the orbital frequency, and you can then also check if there is eccentricity in the data. In fact, we did that, and we find eccentricity is around 0.01, which is something which one could fix with just an iterative procedure. But again, we chose not to do that. We can. There's no particular reason why you couldn't. Basically, start again, take the data, remove the excess or perhaps missing radial momentum, and make this eccentricity smaller. Okay. And so the system is still not, while it works, it's not quite efficient. Basically, we're running with the spectral solve itself takes several days just to solve the problem, and then putting the data on the grid takes several more days. So we certainly want to make that more efficient. But for the moment, since we're using two punctures code as a starting point, it is non-parallel. It's not MPI parallelized. So we split off the solving step from the putting data on the grid, because if you don't want 1,000 processors to all be doing the same thing. So we have one processor that'll do the spectral part, and then we can put 1,000 processors to actually get the data on the grid. We did learn some things. Controlling of high resolution is required, basically because the standard moving puncture gauges forces the black holes to have a small size, and we were exploring different gauge conditions. And there's a paper on arXiv and soon to be in PRD that describes the results.
All right, thank you very much. All right, does anyone have any questions?
Joseph, hi. Did you explore convergence of the waveform at all?
Not yet. Not for that particular one. We did convergence of the waveform for lower spins.
I see. Okay, cool.
So I saw on your slide that you needed to use CC zeta 4. So I guess that means if we want to use these high spin waveforms, we all need to move over.
The reason, so I don't see, well, you can use CCZ4 within the Einstein Toolkit, so it's just choose that. So yeah, is it necessary? It depends on the residual constraints. Basically, if the constraints are small enough and your grid doesn't introduce new constraint violations, then you probably can get away without using CCZ4. Okay, I kind of glossed over it, but there's a big spike in the constraint violation. So at t equal to 0, the constraints are relatively low. By t equal 3m, the constraints get somewhat high. And that is basically having to deal with a high-frequency wave that's not resolved.
So this is numerical?
Yes. And so CCZ4 will then allow you to get physical results out of that simulations, whereas BSSN would just be crazy.
Any more questions? Okay, so I have one I think you mentioned yesterday, but do you have plans for making the code public?
So that was promised in our grant, that it would be.
And the timescale?
I do not know the answer to that.
Okay.
Speak to Carlos.
All right, thank you very much.
Thanks. Can you hear me? Great.
Okay, so the next speaker is Francisco Guzman from Mexico, and he will talk about magnetic reconnection in the sun and gamma ray bursts from Progenesis using Cactus.
Thank you. Okay, so basically I'm going to talk about what our Cactus-based codes are doing and are being applied for. So these are two problems we are working on. So the first one is about coupling radiation with hydro. So we have our own application. We just mounted it onto Cactus just to take advantage of the MPI and I/O infrastructure. So what this code does is that solves the relativistic RRH equations. So as you can see there, you have equations for the matter in the second line and equations for the radiation, and they are coupled through a force field, which contains the information of the radiation matter interaction model, namely the opacities of the processes you want to model. In particular, we can model Thomson, Compton scattering, Bremsstrahlung radiation, etc. And our aim at this moment is that we use a single frequency to model processes, and are at the stage of comparing pure hydro modeling with coupled radiation hydro models. So the state of the art on this is that people in astrophysics, they solve the hydro equations and post-process the results to produce and to model the interaction with radiation. So we are actually doing it on the fly. So we have the radiation, the hydro coupled, and we evolve them simultaneously. So we are so far we are studying the impact of the radiation pressure and all that on the dynamical processes. So what you see here are jets being propagated on a stratified atmosphere. But we are also producing the light curves already of long gamma ray bursts. So here we have a couple of processes playing. So in the first stage, in the maximum of the burst, we have Compton scattering, and in the afterglow, we have the Thomson scattering, it should be. So we are working on fitting the GRBs. Now we are also applying it to gamma ray burst being produced inside a progenitor. So what you see here in the second plot is more or less the density profile of a progenitor. So we are launching jets from there and measuring the light curves. So something interesting of RRH equations is that you can actually integrate the light curve straight from the radiation field flux. So you don't need to post-process anything. So we have pretty clean and sophisticated light curves. So this is something that is in progress still. So what you see here in these colorful plots is that you have the progenitor, the density, and then you have a jet just coming out. So the limitations of our code mounted in Cactus as it is that we are using the unigrid mode only. So we are limited by resolution. Just in order to have an idea of how far we are from the state of the art, these are jets produced by our 2D codes. So this really capture a very interesting structure, and this is what we have with RRH still. So another application we are working on is on solar physics. What we do is the following. So what you have on the left are the equations of the resistive MHD, subject to a constant gravitational field, that of the sun. So this has nothing to do with relativity, or less with general relativity, but the equations are really challenging. So we have resistive MHD, and on the right we have a model of the region of the photosphere, chromosphere, sun interface. And we have a high density in the bottom region and a low density atmosphere in the upper region. And what we have here is just the formation of an spicule. This is a little jet with some properties. It could measure up to 10 megameters. They have been observed. They are observed all the time. And we found that the magnetic reconnection is responsible for producing these jets. So this is kind of a breakthrough. Here's an example of how it works. So the initial data are on the top left here in this slide. We have a sort of an X point. This may be an interesting ingredient in binary neutron star mergers, for instance. If you ever have this type of X points, you probably will trigger the formation of a jet like this. So what you see in the other snapshots is just the propagation of the jet. So, and this is the 3D picture of it, so how the magnetic field lines are modified and all that. So actually, what we are doing is just trying to see how far we can go within Cactus, because we are limited by resolution. So we are wondering whether we can actually exploit the mesh refinement capabilities of Cactus or decide what we are going to do. So thank you.
Any questions? Okay, so I had one. So what do you using finite differencing? Finite volume?
For the RRH, we are using high resolution shock capturing. In fact, it's tricky because when you have high opacities, the system becomes hyperbolic, parabolic. So we are using IMAX integrators so that we keep the stability of the thing. And for the Newtonian case, we are using high resolution shock capturing with HLL-E integrators. So something we are using actually, it's an adaptive choice of HLL-E, C, and D flux formulas. For the Newtonian case, we can do that. So we are only struggling with regions with high betas or small betas as well. So, and but we can control that adaptively. So in Newtonian physics, everything seems to be more, easier. So that's the methods we're using. So.
Any more questions? Okay, then I'll ask another one. So do you see any sort of convergence? Do you get sort of first order, second order?
No, we don't have second order convergence because of this adaptiveness of the flux formula. Actually, we are in between first and second order convergence. And the most we can do here, because we are restricted by the unigrid thing, is checking consistency all the times and just a couple of times convergence. That's for sure. And self-convergence, we have nothing to compare with.
All right. If there are no more questions, nope, then we can thank the speaker again.
All right, good morning. This works, right?
Yes. So the next speaker is Eloisa Bentavernier from the University of Catania, and she will talk about cosmology with the Einstein Toolkit.
All right, thanks a lot. Thanks for this lot. I'm actually not going to use it to present past results so much, even though there's a growing body of them, and some of which have really general interest. What I would like to highlight, though, in this 5 minutes, is that there's a new set of challenges that can be tackled with numerical relativity. And so if you have, you're looking for a new project, you're looking for something that's slightly different, you have some spare cycles, then you can definitely talk to us. And for as long as I'm concerned, today the breakout session will basically be working on this sort of stuff. So at 10 o'clock or throughout the day, just come and join the discussion. The physical motivation of all of this starts with this. So the large-scale universe and its properties. And in fact, this is in itself a simulation. It's one of the kind of best ways to visualize what happens. I'm talking here about sort of properties of the universe at the, let's say, gigaparsec scale and above. And as you may know, this system poses one of the hardest challenges in theoretical physics today, because we know that there's a phenomenology at that scale that is not present anywhere else, and that we don't really know how to explain, because it's in fact so hard to make experiments of and to sort of understand in different scenarios. And this is the one that is connected to dark energy. So we know that that matter at this scale gravitates in a different way than at smaller scales, and this is generally explained with the existence of this fluid, but nobody really knows if this is just an effective way of representing different sort of new physics, new gravity properties, or there's actually fields that are responsible for this. No idea. Now, what we do know is that from, sort of say, our introductory GR class, there's a property of the system that makes it necessary to use, at least in some regime, full relativity, because this system is, under this aspect, not so different from the system many of you study, that of binaries of compact object, in the sense that in both of these cases, you have a compactness, value of the total mass of the system over its extension, which is non-negligible, equal to 1, or in fact even larger. And when that happens, then there are some physical, some properties of the system that have to be described, that cannot be described by classical relativity, meaning Newtonian relativity. And people have become actually quite quantitative about this. You might have seen this work by Tessa Baker and collaborators in 2014, where they sort of map out different observations and where they sit, not only along this sort of potential. This potential is the m over r, say, that I showed before. So not only along this scale, of course, you have systems of increasing m over r, but there's also a second dimension to this, which is represented by the curvature. So I said that those two systems that I showed before have the same sort of potential, but of course have very different curvature, and the relativistic effects will be very different corresponding to that. If you want to use numerical relativity for that, you have to account for that. And so that means in particular that if you want to study these systems, you do need numerical relativity, but a new kind of numerical relativity. And there's a whole set of things. Some of these we found when we started studying numerical relativity, and then immediately thereafter it was told us that, okay, they don't really matter for compact object. And it was this early explorations of methods and ways that you could solve the equations that for some reason did not become relevant for compact objects. Well, some of those will be relevant, and there's probably also something else that will be needed. Gauge conditions, for instance, is one of those fields where the current tools are severely limited. They have to be extended. Boundary conditions, in particular, boundary conditions for a cosmological system are completely different. Matter description, but you can use fluids, you need the particle representation. Initial data is obviously a huge field for this, and just as obviously observables. When you're interested in the system, you're obviously not typically interested in the same things that you look at when you look at sources of gravitational waves. So just to sum up, if you're interested in any of this, like you are curious about how any of these aspects will work, or you want to contribute, just look around for either me or perhaps Jim and Chitian. I don't know particularly how we're going to work, but and I know that there will be something today. And just to sort of give you a starting point for where to maybe get more information about this, and also at the same time highlight how relevant these sort of results have become recently, I'd like to point out to the Physics World May issue, where Jim and his collaborator wrote a paper that made the cover. So that is a numerical relativity cover, a new kind of one, but still a numerical relativity one. Thank you.
All right, any questions?
It's about boundary conditions, exactly, the new numerical relativity. So we are used to, in numerical relativity, to assume the systems are isolated, so we use asymptotic flatness. On the other hand, in the structure formation simulations, we are used to change the topology, periodic boundary conditions. So what are the suitable boundary conditions for?
Yeah, absolutely. So asymptotic flatness is the first thing you can forget about in cosmological simulations. And there's kind of like a shortcut to do something that looks cosmological, is to just do periodic boundary conditions. Algorithmically, they're very simple, but they bring about a lot of trouble when you actually want to establish theoretical results, when you want to know whether an equation has a solution or not, for instance. If you solved it on a compact space, it's completely different. And luckily, people did study this. So there's a lot of works by the same people that did the initial data problem, sort of existence and uniqueness of Einstein solutions of Einstein's equations. They also studied them in compact space. You just have to dig out those papers. But the solution method, the algorithms become a little different then. And the initial data problem becomes very different.
Any more questions? So how many people would you say are working in this field now? Because it's grown quite a lot, I think.
I would say at this point as of order a few tens. So there's at least, I can think of, of course it depends on what you mean exactly working on this field, because many people are interested in figuring out what relativistic effects in cosmology are. Not many of them are doing this with codes, and not many of them are doing it with full nonlinear codes. So there's codes that sort of approach this from a linearized gravity perspective. So there's a full spectrum, it's just not numerical relativity.
Okay.
And I would say there's a handful of groups all over the world, maybe, I don't know, 5, 6, 7 groups that have some sort of code that can be used for this. Not all of them are for the late universe. Some people like to study the early universe for other types of questions. Yeah.
Okay. All right, let's thank the speaker again. Okay, so the next speaker is Jonah Miller from Perimeter Institute, and he will talk about spectral shock capturing. Spectral shock capturing. It's a tongue twister.
So what I'm going to be presenting today is actually the work of a student who's working with me, Joanna Piotrowska. So she's the one who did all the hard work and generated all the plots. So I'm just presenting it, so to speak. So when your problem is smooth, spectral methods have lots of nice properties. They converge exponentially, meaning that if you represent a smooth problem approximately with a sum of functions, then the error of the representation decreases exponentially with the number of functions you use. On the other hand, if you try a discontinuous function, things go very bad very fast. You get a Gibbs phenomenon, and actually your pointwise convergence goes to linear order, and your overall convergence, well, it doesn't actually converge. Those Gibbs oscillations, they move, but they never shrink. So this means that if you try and solve a discontinuous problem, like one with shocks, things go very badly. It turns out, though, that there's a huge family of methods that the applied mathematics community has been studying for a long time, which can at least stabilize the method. So this idea is called spectral viscosity, and it's basically the same as Kreis-Oeglinger dissipation, but adapted to spectral methods. So you add some Kreis-Oeglinger dissipation to your right-hand side, modified with this window function Q, which allows you to adapt to the polynomials that you're using for your representation, or whatever functions you're using. And this stabilizes the method, so you can run without your code crashing. The phase of the shock is correct, and you get self-convergence at exponential order, but you do not get true convergence. So you still converge to the correct solution only linearly. Also, it's not total variation diminishing, so you get wild oscillations across the shocks, as you would if you naively tried finite differences to solve a shock problem. And the Gibbs phenomenon is still there. So the question would be, can you take this? There's something spectral going on here. You're still getting self-convergence. So is the information in the representation still there that after the fact you can reconstruct your true solution with spectral accuracy? And there are, in fact, results that show you can. It's just no one has actually tried to apply them in a real physics situation. And so one approach, there are many, is to convolve by a window function. So this is essentially a smoothing or a filtering approach, but the windows function's structure and shape change depending on the number of modes you use, and it changes depending on where you are in space. So if you had if, for example, you were trying to evolve a shock, or two shocks, one at like minus 0.4 and one at 0.6, then you would convolve across in the region where you're basically near the shock, you have one-sided, the window function is one-sided. And if you do this, and you vary the size of the window function as you change the resolution, you can actually recover a smooth solution. A solution with shocks in the right places. So here's some results for that, where Joanna just took a step function, or two step functions, intentionally broke it by projecting it into Chebyshev polynomials. So you see the Gibbs phenomenon in blue. And then she filtered it with this convolution, or mollified it, I guess, and she got the red curve. So the red curve here is not the analytic solution, it's the reconstructed solution. And by eye, it looks pretty nice. It doesn't do perfectly near the shock, but it does sort of roughly what you'd expect for a high-order shock capturing method. Sorry, high-resolution shock capturing. And it also actually converges to higher than first or second order. So with the single shock, Joanna was actually able to attain spectral convergence. She was far from the shock, she was able to recover that. The error near the shock is of order 1. This is essentially because there's a slight phase error. Basically, when you do this reconstruction, you have to approximately detect where the shock is before you can do this one-sided thing. And if you're a little bit wrong there, then your reconstruction fails right at that spot, basically because the phase error becomes an order 1 error no matter what you do. And even in the case where there's 2 shocks, she actually is able to recover 4th order convergence, despite the physical discontinuity. So just to summarize, high order convergence is possible with spectral methods even for discontinuous functions and fluids and shocks. However, the implementations basically don't exist. Essentially, there's only been toy codes and theorems and proofs, but we're trying to work on that. It will take some time. We're not production ready. We need to do some more experimentation to figure out the best way to go. But I think it's a promising approach. That's all I have.
Any questions? Roland?
So how tough is this to make this thing work in 3 dimensions?
Yeah. No one's done it in 3 dimensions, so I don't know the answer to that yet. But my hope is that you can just do a Cartesian product type approach where you mollify sort of dimension by dimension, and your shock position is going to be less clear, so you have to somehow interpolate or extrapolate to figure out where it is. This method, I think, is much better than the other approaches for that because it's a bit robust against error in the position of the shock. There are other approaches that fail spectacularly if you're a little bit wrong.
Anyone else? So how does this relate to solutions with discontinuous Galerkin methods, which are trying to solve a very similar problem in a very similar way?
Right. You can think of this as sort of in post-processing turning your problem into a discontinuous Galerkin method, because you do a global spectral method, and then after the fact, you sort of approximate your solution as piecewise smooth as opposed to globally smooth. But as far as implementation goes, it's quite different because you're assuming global smoothness. Shock capturing for discontinuous Galerkin methods, basically near a shock, it turns itself into a finite volume method. Whereas here, you're really trying to do spectral everywhere.
Any more questions? No? Then we can thank Jonah again. All right, so the next speaker is Daniel Johnson from here. And he will talk about Python open source waveform extractor, an open source Python package to post-process numerical relativity simulations. Very good. Go ahead.
Hi. So I'm an undergraduate student here at Illinois. I study computer science and physics. And I've spent the summer working on running simulations and extracting extracting strain and at null infinity from these numerical simulations numerical relativity simulations that we've been running. We have also been developing a Python-based waveform extractor. And the motivation for this comes from that Python is widely available on all high-performance computing environments. Our previous, and we run our simulations on Blue Waters, which is a supercomputer here at the University of Illinois. And we had some problems running, or we run simulations on blue waters. This is kind of our workflow. We run it on blue waters, and then to actually get the extracted waveforms, the extracted strain from our simulations, we had to copy over all of our simulation results to an environment compatible with Mathematica, because we would run simulation tools to extract, to get the strain out of the simulation results. And a couple problems that we had with this was that we had trouble licensing Mathematica. So as undergraduate students, me and some of my fellow interns this summer had problems getting our hands on like a copy of Mathematica that we didn't have to pay for. So there was some trouble with that. So again, we would copy over simulation results to our campus cluster. It turned out that that was our environment compatible with Mathematica. And then we would run simulation tools to actually get the extrapolated strain at null infinity. And so that's our first motivation of wanting to have a Python-based extractor, so we could run it on the same environment as the environment that we were running the simulations on. But we also wanted to have work with open source software so that we could know exactly what's going on at every single step. So there's no black boxes, so we know down to the smallest function, the interpolating function, anything. We know exactly what's going on in each step. So some of the applications of Power, the Python open source waveform extractor, it's based off of simulation tools, as I mentioned before. And it's based off simulation tools because this Mathematica package, because we've found that from our results in the past that it's a very robust solution to carry out this analysis. So when we were developing this extractor, we depended heavily on the workflow and simulation tools. And as I mentioned before, it can be run on the same high-performance computing environment as the simulations we are running. And this allows us to run it as a health monitor. So we can check the strain in real time as the simulations are running on blue waters, which has been very helpful. So in the past, what we've done is we've just used like the puncture trackers, and I looked at the separation distance between the two black holes, and this kind of worked, but it kind of led to a lot of guessing of like, okay, so it merged here, but it's going to reach the detector like here, so it was kind of more of a guessing game, and this gives us a more concrete way of determining if our simulations are actually done. And then it's been streamlined so it can get very specific data. So it takes a quick amount of time to get to extract our entire catalog of simulations that we've been running. So just a quick couple of plots. On the left side is a comparison between Power and simulation tools. So you'll see that it overlaps almost, very well. And on the right side, you'll see the difference, the Power strain minus the simulation tool strain, so the delta H. And just to point out, the scaling on this is 1 × 10⁻⁶, so it's about 5 orders of magnitude smaller. And this is for a mass ratio 1 low eccentricity system. This is again another simulation that we've been running. So the difference between the two is very small. And this is for a more eccentric, higher mass ratio system. And that is all I have, so thank you.
Any questions?
Where can I get it?
So this is going to be posted on the archive next week, and at that time you will be able to clone the repo.
Anything else?
Oh, by the way, sorry, the actual plan for this, I don't know whether Daniel mentioned that, is to implement this as part of the Einstein Toolkit so that any users that get the code also have the ability to do this on their clusters, local clusters.
I was just wondering, this is post-processing with a script. Would there be any benefit to it being a Einstein Toolkit thorn that could be calculate this at real time as part of the simulation?
I don't know. Yes?
So that actually relates to one of the questions I was going to ask. So you said that you were able to monitor the strain in real time, but the strain is computed using Fourier integration, which means that you need the entire Psi4 waveform before you can get it. So I think you can't be computing the strain in real time, and it doesn't make sense to run it online.
Okay.
You could probably be looking at Psi4 maybe.
We definitely can look at Psi4. That's
well,
true.
you can. We're already doing this. We were using Psi4, but as you say, you need all the information to get good quality waveforms. One other thing that Daniel is not saying is that you can compute the convergence of the many different resolutions that you are running for your waveforms. And you can get from the get-go, after a few hundred M, whether you have the sufficient resolution for the campaign. And if not, then you can save a lot of computational time and then just start maybe another higher resolution. So this is the purpose of the health monitor. And of course, once the simulation is done, then you know whether you have sufficient information after merger to have a nice waveform.
And maybe just to clarify, I guess by real time, what's meant is not every single minute, but every day once the simulation has written a checkpoint, you can do that. And as long as you taper, I guess you get something that you can Fourier transform for the strain. It's not going to be perfect, and you could just do the time integration if you want. It's really just something you can do it, and you can see what your strain looks like. Mostly, I guess you want to do the convergence testing to see if that works nice, just in case. But yeah.
Okay, well, thank you very much. So, I don't have anyone else on my list. So is this the end of the session, Roland? Okay, well then I guess coffee time?
Well, there's coffee outside still, yes. And otherwise, then we would start the breakout sessions right away. So Gabriel wants to do a little bit of the introduction, I guess.
Yeah, so, I mean, maybe it would make sense to have coffee and then come back and do that at 10:15. Would you think so? Otherwise people won't know when the different sessions will start. I did I have another announcement. Maybe we can do that at 10:15. So let's break, come back at 10:15. The slide that just went up was Xin talked about the data vault. She had a survey that you might have already seen that led into the design that she did. If you didn't have the opportunity to fill out that survey and would very much welcome if you have 10 minutes to spare to do that, it's at this URL here. It just asks a few questions about your ideas and needs for curating and storing and finding data from the Einstein Toolkit. So let's meet back here at 10:15.
So is there a list of the breakout sessions and how it's going to be organized?
Well, that's what I think. When we come back at 10:15, what I'd like to do is to make a list of what are the people's breakout sessions that they're suggesting, and we can cluster people. We'll have some. I think we have. What time is lunch, Roland? Lunch is at noon. So we'll have one. Let's get back promptly at 10:15. We'll have two breakout sessions then before lunch.
you.